Okay, so for this video, we're going to continue on 5.2, which is the definite integral. And in the last video, we talked about the definition of the definite integral and how we can rewrite the the integral in terms of the Riemann sum. And so recall, let me move this example downward so that I can show you what to recall. So recall that if we have the integral between a to b of f of x, or the area under the curve, that's going to equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of xi times delta x. So we did an example last video about this, and now we're just going to do a few more and introduce a couple new concepts in this video, and that'll be it for 5.2. So this is what we defined the integral, or the area under the curve, as, where our delta x was equal to b minus a all over n. And that the goal was to find xi, you would do a plus b, you would do a plus delta x times I. So in other words, you can replace that xi as a plus b minus a over n times I. And so the goal is to find our xi, plug it in, and then evaluate the sum as n goes to infinity, and we use those nifty summation formulas in order to manipulate them. So that's exactly what we're going to do. So let's take a look at this example. This example says, find the area under the curve of y equals 1/2 x plus 3 between 2 and 6. Okay, so the first thing we want to do is, since they want the area under the curve of y equals 1/2 x plus 3, in other words, we can rewrite that in terms of an integral, which is actually a great idea. So we can get used to this. We have the integral from 2 to 6, because remember that the integral is between from a to b, and this is our a and b. That's the interval we're looking at. And then we're going to write our function inside, x plus 3. And then don't forget the dx. That's important because that tells us what variable we're integrating or finding the area under the curve of. Okay, and then this is going to equal, using that definition, the limit as n approaches infinity from I equals 1 to n of f of xi delta x. So now our goal is to find, 1, we need to find delta x, and then 2, we also need to find our xi. So our delta x, we said over here, is b minus a over n. Here our b value is 6, our a value is 2, and then we divide by n. So this tells us that our delta x is going to be cut by 4n. So our width is going to be 4 times n, and we don't know how many n values we're going to have. We want to take it to infinity to get the most accurate approximation. So that's what we're going to do. And then for our xi, we are going to do a plus b minus a all over n, which, since we already calculated b minus a, that's right there, we can just say a, which our a value is 2, plus 4n times I. Okay, perfect. And so here, now what we're going to do is, now we're going to rewrite the sum is going to equal the limit as n approaches infinity from n I equals 1 of f of xi, and since xi is equal to all of this, we're going to plug it into that value there. We're going to get 2 plus 4 over ni. I just took the parentheses off. times delta x, which delta x is equal to 4 over n. Beautiful. Okay, so now after this, what we want to do is we want to substitute that into our function because we have an equation for our function. Our function is over here. We're going to plug this into the x value of our original function, or the function we're integrating from, and we're going to get the limit. And notice how I'm still writing this notation here. I haven't took away the limit and I have not took away the sum because I haven't done anything to be able to take that away. This is strictly equal to this next part, and it's crucial that you write the limit because you haven't evaluated it at infinity yet. And so my function was 1/2 times x. So for my x value, I'll write 2 plus 4ni. So for my x value, I'm just putting that in. So here I have 1/2 x plus 3. Here I have 1/2. My x value is now getting replaced by my xi, which we found here. And then it's going to be plus 3. And that's our f of xi. That's our piece here. And now we still need to multiply that by delta x. And remember that delta x is equal to 4 over n. So very nice there. Okay. Now after this, I would highly suggest simplifying this so that we can evaluate it, because at the end we want to evaluate this sum and hopefully replace our I by one of those nifty formulas that we found earlier. And so now what I want to do is I want to distribute this 1/2 over because it's in my way. And so we're going to write the limit as n approaches infinity from I equals 1 to n. And then if we distribute 1/2 times 2, that's just 1, plus 1/2 times 4n, that's just 2ni. And then we still have that plus 3, so hold on. And then we still have that plus 3 at the end times 4 over n. And so I'm just being very careful with my steps here so that you can see where we're at. And then our next step is to simplify a little bit more. And so let's simplify. I'm still writing the limit because I haven't done anything with that yet. Then I'm going to add these two together. And I get, I'm just going to do this, 2 over ni plus 4. But this is still getting multiplied by 4 over n. Okay. So after this, what we're going to do is I would suggest distributing this 4n over inside. So we want to get this 4n and distribute it inside. But I'm going to go ahead and do that on the next page so I'm not all crammed up. So I'm just pasting that over so that you can see it. Okay, and so if I distribute that over, we're going to get the limit as n approaches infinity of the sum from I equals 1 to n. Distribute that 4n, and then we're going to get 8 over n squared I plus 16n. Okay, so after this, what we want to do is remember that we can actually take this out, and this is all inside that sum. So these are all still in part of that sum that's right here. Okay, so we have two choices here. We can break this up and write this as one sum plus the sum over here as well. Or we could also recognize that this has nothing to do with I and this has nothing to do with I. And this is the only thing that has to do with I. And in the last video, in the example, we noticed that when we have I, or I squared or I cubed all by itself, we'll replace it by one of those formulas that we learned earlier. And so what I can do now is I'm going to replace this I by its formula. So I'm going to replace I by n times n plus 1 over 2. Because remember that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. And so I can go ahead and replace it now. But just so that you know this is actually equal to n. Actually, let me write it like this. Since that 8 over n squared has nothing to do with I, I'm going to pull that out of the first summation times the sum of I equals 1 to n of I, and then plus, this technically has its sum itself, which is the sum, plus the sum of, actually, let me write it here, plus the sum of I equals 1 to n of 16 over n. But here's the thing. This is basically just a big old constant right here. And so recall that if you have a sum with just a constant, it's going to be that constant times n. So because this is just going to be a constant times n, the constant itself times n, I can actually rewrite this so that it's going to be 16 over n times n. And so these are going to cancel each other out right here. And so then we can rewrite this as the limit as n approaches infinity of 8 over n squared times the sum from I equals 1 to n of I plus 16, because they canceled out right over here. Okay, beautiful. And so now after this, what we're going to do is now we can replace this by this. Again, like I said, if you've seen it ahead of time, you could have done all that up here. And so when you get more comfortable, go ahead and do that. But it's good to write down all the steps when you're first learning them. Okay, so let's keep going. Now I'm going to replace that I, the sum of I equals 1 to n, by its appropriate formula here, so we can evaluate. So this I times n squared is still going to be here. But now instead of writing this sum, I'm going to write n times n plus 1 all over 2. And then it's going to be plus 16. Okay. And now after this, now notice I didn't write the sum again because I didn't need to. The sum is equal to what it is up here, and I replaced it right here. So that was just fine. Now from here, we want to evaluate the limit as n approaches infinity. And you could do L'Hopital's rule, but like I said before in the last video, you know that you have n squared here, you have n squared down here. And so basically you're going to have 8n squared for the leading coefficients. That's not what it's actually equal to, but you'll have 8n squared over here divided by 2n squared down here. So if we simplify this and we approach infinity, right, if we're doing L'Hopital's rule, we'll hit that simplification at the same time. And so what we're going to do here is that this is going to end up being 8 over 2, which is the same thing as 4. So this is equal to 4 plus 16, which is equal to 20. So that's what the area under the curve is between 2 and 6. Okay? And so now what I want you to do is I want you to try on your own y equals, so find the area under the curve for y equals 3x between 0 and 4 using that definition of an integral. Okay, so I'm not going to go over this just because it's going to take a while, but it's good practice. The answer here is going to be 24, so do it on your own. And now we'll go over another example. Okay, so we have done it. We have found the area under the curve using Riemann sums. And so I just want to point out that we don't always have to use Riemann sums if we can use geometry to do it. But we can always resort to doing it using Riemann sums. But sometimes it's easier to do it geometrically. So what do I mean by that? So let's say we had the area under the curve. We wanted to know the area under the curve for this problem. So we want to know the area under the curve for the function x plus 1. So this is just a line between -2 and 3. Of course, we can do it using the definition. So let's go ahead and practice using that definition. I'll do it quickly. So using the definition, we would write that this is going to equal the limit as n approaches infinity from I equals 1 to n of f of xi delta xi. And now to find the width of the function, so for our xi, or for our delta x, we need to find the width. And so the width is b minus a all over 2. My b value is 3. My a value is -2. Oh, it shouldn't be b minus a over 2. It should be b minus a over n, sorry. Over n. So at the end, we'll add these two together, and our width is going to be 5 times n, which makes sense because between -2 and 3, there's a distance of 5 between this. Okay, so this is going to be our delta x, and now to find xi, we would do a plus delta x times I, and since we already know delta x, we'll just plug that in. Our a value is -2. Our delta x value is 5 over n times I. So this is going to be our xi value. So in other words, we can rewrite this definition to be the limit as n approaches infinity from I equals 1 to n of f of xi. So our f of xi is, and I'm going to rewrite it in this order, -2 times delta x, which is 5 over n. And now if we wanted to, oh wait, I forgot something. Oh no, I didn't, that's fine. And now what we're going to do is we're going to plug this in to our function. We're going to plug this into our function, and our f of x value here is x plus 1. And so now we're going to get the limit as n approaches infinity, and now we're going to replace f of x by its actual function, x plus 1. Our x value we're replacing is 5i minus 2. So this is going to be x plus 1 is our function. So it's going to be 5ni minus 2 plus the 1 on the outside, and then times 5 over n. Okay, beautiful. And so now we're going to get the limit as n approaches infinity from I equals 1 to n of 5 over ni minus 1 times that 5 over n. Okay, so now after this, what I would do if I were you is, I didn't do this in the last example, but I definitely could have, but I just wanted to show you different ways to do it, is instead of distributing this 5n in, what I'm going to actually do is I'm going to take it out of the summation right now because I can. I'm summing this all together times this 5n so we can pull it out. And so this is going to be the same thing as, and bear with me, the limit as n approaches infinity of 5 over n times the sum from I equals 1 to n of 5ni minus 1. And now in the last example, I showed you how to actually do the simplification. So here I'm actually going to go a little bit faster and just go ahead and replace this I already by n plus 1. So I'm replacing the sum of it over 2. And here a constant times a constant inside a sum that has nothing to do with it is just that constant times n. So I'm going to replace this by 1 times n. So then when we evaluate this, we'll get the limit. The limit's still here. I haven't done anything with the limit, but now I'm replacing that sum. So I still have 5n on my outside, and I still have this 5n that was attached to this I, so I'm going to leave it. I'm going to have 5 over n, and now I'm replacing that I by that Gaussian formula, n times n plus 1, all over 2. And then this is going to be minus 1 times n, which is just n. And so now I've replaced everything by that. Okay, perfect. And now what we can do is we can actually just evaluate this. So what you can do here is, yes, you can distribute that 5n over. And if we distribute that 5n over to both values over here, we'll get the limit as n approaches infinity of 25n squared times n plus 1 over 2, and then minus 5n times negative n, which is going to give me negative 5n over n, which is the same thing as just 5 itself. So I don't really need to write that. And so now my goal here is I have to now evaluate this. And like I said earlier, I have an n squared term up here, an n squared term here. So what is actually going to happen is we're going to take the leading coefficients, because if we apply L'Hopital's rule, it will end up as that. So this limit as n approaches infinity, since they're approaching infinity at the same time, looking at the leading coefficients, is going to be 25 over 2 minus this 5. 25 over 2 minus this 5. Which is equal to 15 over 2. And so that was the answer that we got using the definition of a definite integral. But we don't always have to do it like that. And in fact, when you can, and you can't always do it, is that you can actually do it geometrically. Because if I'm just going to write down this function again. If I write down the integral from, what was the integral from? Negative 2 to 3 from x plus 1 dx. Well, if I go ahead and actually graph this function, let's graph it. Here at negative 2, and then at 3 over here. At negative 2, if I plug that into x plus 1, I'll be at negative 1. So I have a point here, and it's just a line. And then for 3, we'll be at 4 if we plug it in. So this is a spot 3, 4, and this is the spot negative 2, negative 1. So here we just have this line here. And here this is 1. And so remember that when we're integrating, we're actually looking for the area under the curve, right? So because we're looking for the area under the curve, what we can do instead is, if I go ahead and draw lines here and a line here, the area under the curve is going to be equal to this area here and this area here. And notice here we actually just have 2 triangles, so we actually didn't need to go about it using our Riemann sums. or our definition formula. We could have just drawn the picture. So whenever you know the shape of your graph, drawing the picture can actually be helpful because you could have avoided that. Because if I call this, let's say, area 1, and then let's have this one be area 2, the total area of this is going to actually equal area 1 plus, going to be area 1 plus area 2. Well, area 1, we can just use 1/2 base times height. But I want you to notice something. When we're looking at area, if we are under the x-axis, we're actually going to be negative. So for area 1, so this is the only time where it's okay to have negative area when we're evaluating an area under the curve, because we're in the xy plane. So for this, we're actually going to have, since it's under the curve, it's going to be negative 1/2. And then base times height. And so my height here is actually -1. If you see on the y-axis, this has a height of it has a height of 1. And this has a height of 1. So it's going to be 1 times 1. So that's my first area. And then my area 2, we can also use our triangle because this is just a right triangle. And now our distance here is 1. And then we have 3 on this side. So it's going to be, my base here is actually 4. And then my height, if I look at my y-axis, is also 4. And so now I can evaluate that integral. So this integral gives me, this part gives me -1/2. Here, this part is going to give me 8. And so when I evaluate that and I sum that up, I actually get 15/2, which is exactly what we got when we use that definition. So the definition does take up a long time. So just be aware of that. If you have a function when you can do it geometrically, then go ahead and do it geometrically. You don't need to go about it the longer way. This is much shorter. And so another example of when we can do it geometrically is if we have, it is getting dark in here. If we have the integral from 0 to 5 of the square root of 25 minus x squared dx. And so for this example here, if we look at this function here, it's kind of weird, and actually it would be actually almost impossible to do it using Riemann sums without adding additional formulas, because we have a square root function. It won't be as easy, like it's going to be stuck in a square root. And so at some point we're going to have the square root of I, which we don't have a formula for. So we don't want to do that using our Riemann sums. That will be crazy. But if we think about what kind of formula this is this is actually a semicircle. If you recall, this is the semicircle with radius 5. So here I'm at 5, 5, and 5. So this graph gives me this semicircle of 5. And they want the area between 0 and 5. So they want the area here. This is what they want to know. How much area do I have here? And here's the thing, I can't really use Riemann sums here. Or I could, but it's going to be just a mess. But because we remember geometry and we recall that the area of a full circle, so area of a circle, full circle here with radius r is equal to pi r squared. If we are just looking for a corner, or a quarter of this, then this here area is going to be 1 over 4 pi r squared, because we're cutting that area into a fourth. Just like if they ask what's the area between -5 and 5, instead you would do 1/2 instead of 1/4. And so the area of this is going to be 1 over 4 pi, r squared is 5 squared. So it's going to be 1/4, it's going to be 25 over 4 pi. And so that's our area. Much easier than doing Riemann sums, but you can't always do Riemann sums. Like you can't do Riemann sums. You can't always do it geometrically. You could do it geometrically for things that you can look at the shape and go, oh, that's a triangle. I have a formula for that since they want the area. Here it's a semicircle, but you know the area of a circle and you can manipulate it that way. But for instance, for a parabola, there's no way that you can get that without getting the exact answer for that area. So we still need to use Riemann sums for that. So what I want you to do next is I want you to actually try one on your own using 2 different ways. Actually, I'll do the easier way with you so that you can see it, and then I want you to practice it using Riemann sums. So, for example, if I have I want to find the integral, the area under the curve from -2 to 2 of the absolute value of x dx. Now, we can do this 2 different ways. Now, if I graph the absolute value of x, I have a V shape, and here I'm at -2, 2, and 2, 2, because they wanted it from -2 to 2. Now, if I look at the area under the curve for this, it's going to be this area here plus this area over here. So geometrically, it's kind of easy. I have 2 triangles. I add the area of this triangle times the area of this triangle. Easy peasy. You can also rewrite this to be, and this is how I would do it when you're going to do the Riemann sums, is rewrite it so that it's -2 to 0. So miss my a value to my b value here of -x dx. And then I'm going to add this other piece here, which is going to be from 0 to 2 of x dx. And so now if we add them all up, right, I'm going to get 1/2 based. So I'm going to do it geometrically, but I want you to try it using the original definition. It's going to be 1/2 base times height. And notice these areas are actually going to be the same, so we really could just find one and add the other one. So 1/2 base times height, my base here is going to be 2, and then my height is still 2. And so for one of the triangles, I get 2, but I have another triangle. So my area 1 plus my area 2 is actually going to be 2 plus 2, because these are the exact same triangle, which is equal to 4. So I just did it geometrically. You are welcome to do it. Actually, I encourage you to try to do it using the Riemann sum so that you get extra practice. And it's super dark in here. So that you get extra practice. But yeah, it's not too bad. So whenever you can do it geometrically, please do it geometrically. I don't need you to get all crazy with it when you don't need to. Okay, hope that made sense. Now what I'm going to do is I'm actually going to go over properties of the definite integral. So for the properties of the definite integral, so for our properties of the definite integral, I went ahead and wrote them all so that I save some time, is that if we have the following, so if the following integrals exist, then if we have an integral from b to a, which is weird because normally we have the integral from a to b, then we can rewrite it as negative a to b. So that's all that's saying is that if they give you it from b to a, what you do is you rewrite it in terms of a to b, but now you have to tack on that negative sign. That's all that means. And then for that next one, it's just saying that if you have the, integral from a to a of f of x dx, then that's just 0, which makes sense because if you're looking at the area under the curve at one spot, you're not going to get an area. There's nothing there. Another thing is that if you have the integral from a to b of c, that's just going to equal c times b minus a, where c is any constant. For this one, I'll actually give you more reasoning in the next section, but for now, just know that this is what it is. I was going to go over all the proofs, but because of our lack of time in this course and with everything going on, I decided to opt those out for now. But again, if you want to see the proof, come and join my office hours and I'll be happy to go about these proofs. Okay, so for this one here, this is saying that the sum of the integrals is the integrals of the sum. Oops, I thought I had the highlighter on. And the difference of the integrals is the sum of the integrals is the integrals of the sum. And so we can do the same thing with the differences as well. I said that really weird. That just means you can break them apart. And then what we can also do here is we can do that if you have a integral that's from a to c and c to b, then we can rewrite it as a to b. And then you kind of seen this in the last example. That's what I did here is I had an integral from -2 to 2, right? And what I did was instead I rewrote it from -2 to 0 and 0 to 2. So nothing too crazy. So let's use some of these properties to evaluate some integrals. So these will be quick. So let's say we want to evaluate the integral from pi over 2 to pi over 2 of cosine x dx. Well, let's look at our properties. We're going from pi over 2 to pi over 2, so we're staying the same. So actually that area is going to be equal to 0. Okay, so let's do another one. Let's say that if we have the integral from 0 to 10 of f of x, I don't know what f of x is, and let's say that's equal to 17, and we have the integral from 0 to 8 of f of x dx, and that is equal to 12. Let's say we want to find, or let's say, oops, we want to find the integral from 8 to 10. So what they did here is they gave us the integral from 0 to 10, and then they gave us the integral from 0 to 8. And they want to know what the area under the curve is from 8 to 10 of, and I should write dx there, of f of x dx. So they want to know that area under the curve between 8 and 10, but we only know the area between 0 to 10 and 0 to 8. So how do we find this area? Well, if we actually look at that very last property here that says that if I have the integral from a to c of f of x dx and the integral from c to b, then that's going to give me the entire area. Well, here I'm given the entire area, and I know one of those pieces and not the other one. So let's rewrite it using that property. So we would write my integral from a to b is going to be 8 to 10, sorry, not 8 to 10. It's going to be 0 to 8 of f of x dx plus my integral of 8 to 10, right? So we have the integral from 0 to 8 plus my integral from 8 to 10 of f of x dx, and this should equal the integral from 0 to 10. So if we have the integral from 0 to 8 and the integral from 8 to 10, then that should equal the integral from 0 to 8 of f of x dx. So notation here is really important, especially on the dx. And we actually know the value of this. This value here is 12. We don't know this one, but it's okay. That's the one we're looking for. And we know this one, that one was equal to 17. So now we can evaluate that last integral. So the integral from 8 to 10 of f of x dx, move this 12 over to the other side, is going to give me 5. Okay, perfect. And now the last thing I want to go over is what are called the comparison properties for an integral.